Welcome back. In the previous class, I was talking about the differentiator design, and we have seen first order differentiator, that is basically based on the Woodkins first order sliding mode control. We have also explored the high gain based differentiator. In this lecture, I am going to extend the concept of differentiation that is based on the higher order sliding mode control. And why basically we are looking for differentiator based on higher order sliding mode control? Because accuracy of differentiation in presence of noise, it is possible to show that is very high, and somehow that differentiation process is robust and exact. Okay, so main theme of this lecture to talk about robust exact differentiator developed by Professor Levant. So purpose of discussion, I am going to talk about the first order differentiator. It means that suppose I have some kind of signal that is yt. So now I am going to develop some kind of algorithm such that if I substitute yt, then I will get y dot, and in this way suppose I have second order system, then I can able to design control based on the output and their derivative. Another important thing, most of time this particular output is measured using the help of sensors, and we already well aware that sensor is containing several noises. So how to get differentiation of the noisy signal? Obviously most of time I have high frequency noises, so high frequency noises signal such that I can able to get some kind of exact differentiation. So it means that differential process I have to actually finish in presence of the measurement noise, some kind of measurement noise. We know the characterization of noise, and after that we are trying to develop some kind of differential process based on the higher order sliding mode control. And since I am just interested in calculating first order derivative, and due to that reason this is called first order exact differentiation process. Why exact? Because this differentiator will work in presence of the measurement noise also, and we can able to actually get true derivative in finite time if I will use these kind of concept. And obviously in presence of some kind of measurement noise, whatever differential things we will get, it is possible to show that we will get with accuracy. And why basically we are doing this? Because I want to design some kind of output feedback based control. So I have second order uncertain system, so some kind of black box system I have. What is meaning of black box? I just know the order of system, but I don't know the dynamics completely. So suppose that I have some kind of input and I am measuring here output, and now whatever ut I am going to design, that is function of yt and y dot. So that kind of things we will see, and it is possible to show that differential process can finish in finite time. So I can able to design finite time controller based on this. Okay. So first I am going to tell you the problem statement, because most of time we have seen that in control system, whenever we have output, so basically we are measuring output with help of sensor. Okay, and that is corrupted by some classes of noise. So I am going to define some classes of noise which is commonly occurring in the system, that is called bounded Lebesgue measurable noise. Okay, I will define what is meaning of bounded and Lebesgue measurable, and what we are assuming that whatever signal I am going to develop some kind of algorithm such that if I apply f0, then I will get f0 dot t. So that will satisfy some kind of assumption, and one of the common assumption is Lipschitz assumption. It means that suppose I have to calculate the first derivative of f0, I am assuming that first derivative is continuous. I am also assuming that second derivative is also continuous and bounded by some kind of Lipschitz constant L. Okay, that kind of assumption I have. And what is our main intention? That if this signal f0 contains some kind of bounded Lebesgue measurable noise, I will define what is meaning of Lebesgue measurable, then I have to get the differentiation. Okay, and due to that reason, what is requirement? Differentiation process should finish in finite time and it can handle some kind of non-smooth signal. So let us first characterize the meaning of bondedness. So meaning of bondedness here, that whatever noise I am going to consider with the signal, so that has finite amplitude. So suppose that I have f0 and some quantity like n alpha sin omega t. So whatever alpha I am assuming, that should be bonded. And Lebesgue measurable means noise can integrate over any time interval. So if you consider any time interval here, suppose that interval is t1 to t2, so I am assuming that whatever noise here, that should be integrable. So that kind of noise is going to enter inside the system, or whatever differentiator I am going to develop, that is only applicable for that classes of noise. Okay. Now this is the definition of the bondedness. So here it means that some kind of m I know, and after that, why this assumption is required? Because somehow whatever process I am going to develop, and after differential I am going to utilize that as a control design. So actually differentiator as well as our closed loop system is running in some kind of closed loop. Obviously differentiator is running inside computer, and somehow output of the computer we are getting the derivative of output, and after that we are applying to design the control, and due to that reason we have to make sure that everything remains the bonded. So using this condition I can able to prevent our system to destabilize. Okay, and this is just a simple example. Now Lebesgue measurability. So I have already told you that whenever we have some system, so generally system is represented in form of the differential equation like this, and suppose I have some noises here, for example. So in order to get the information of state evolution, I have to integrate the right hand side of differential equation. So most of time, if something is integrable, then it is possible to show that always there exists a unique solution, or at least existence I can able to give guarantee. And due to that reason, for broader prospect, I am assuming that whatever noise that is going to enter inside the signal, that will satisfy this kind of property. Okay, and obviously if Lebesgue measurability is there, then theoretical proof of control, once that is coupled with differentiator, that is easy. Okay, and due to that reason, basically whenever we are considering noise, at that time we are considering these two conditions, one for stability, another somehow for give the mathematical guarantee in presence of some kind of noises. And obviously in realistic world I have sensor and environmental disturbance, and it is possible to show that these kind of disturbance will satisfy all above property, and you can just consider some kind of noise which is periodic in nature. Okay, so you can able to represent that noise in form of constant, sine and cosine, and it is possible to show that that is going to satisfy these two assumptions easily. So now let us come to the original problem statement. So I have original signal f0t. Okay, but whatever signal that is coming to the system, so that is corrupted by some kind of noise eta t, and again I am assuming that eta t is bonded and Lebesgue measurable. Now I have to get f dot 0 t, but originally whatever signal I am applying, that is ft. So main intention that even if I will apply ft to the system, but how to get derivative of f0 dot, okay, with some kind of accuracy. Obviously exactly I cannot able to get, you cannot able to develop some kind of algorithm exactly you can able to differentiate in presence of some kind of noise, but with some kind of accuracy you can able to do this job. Okay, so in order to do that, what I am going to do, I am going to consider some kind of system. Suppose that z0 equal to v, and what is meaning of z0? Suppose that if I have to differentiate some signal like f0t, because this is somehow original signal. So first I will develop theory for some kind of system where there is no uncertainty or disturbance, and after that I will actually check the performance of algorithm in presence of noise. And due to that reason I am assuming that I have to differentiate this signal f0t, and after that differentiation of this particular z0 dot is nothing but f0 dot that I have to obtain. Okay. So, for that what I am going to do, you can see here that I have developed some kind of first order system z0 equal to v. V I am going to define eta 0 is nothing but the difference between z0 and f0. Now, I have to maintain second order sliding across eta 0. What is meaning of second order sliding mode control? It means that eta equal to 0 as well as eta dot also equal to 0 in some kind of finite time t equal to t. That is the meaning of second order sliding mode control. Obviously, in this process I have to design this signal v that is somehow follow the property of flip-flop solution. Okay. So, now what I am going to do, I am going to assume z equal to f0, f0 dot equal to v. What is f0? That is also equal to z0 dot. Now, what I am going to do, I am going to take derivative of eta 0. So, eta 0 derivative eta 0 dot minus f0. I am assuming that whatever signal I am going to differentiate, that is differentiable, and after that z0 is nothing but v, and I have keep this assumption. Okay. In this way this differentiator is somehow different from the Professor Utkin's differentiator that is based on the first order sliding mode control. It is possible to show in case of Professor Utkin differentiator, assumption is just this should bonded by some constant m. Okay. But in order to apply higher order sliding mode control, you should know the second derivative that is also bonded. It means that if signal has just first derivative, you can not able to apply this kind of algorithm. That is the limitation. Okay. Obviously, whatever algorithm that is developed in control system, always that will work in some limitation. Now, v I am going to define such a way such that I can able to enforce sliding mode across eta 0. That is our main goal. And due to that reason, now you can see that z0 dot, which is v, because this system, now I know I have to make sure eta equal to 0 and eta dot equal to 0. So, same kind of term I am going to keep here. Okay. Now, if carefully you can see, this is nothing but some kind of super twisting like algorithm. That is obviously not exactly super twisting algorithm, because in super twisting algorithm whatever term here, same term you have to repeat here as well as here. Okay. But here if you see carefully, then suppose that if I will define some kind of term that I have defined here eta 0. So, eta 0 is nothing but z0 minus ft, and if I will calculate the first derivative of eta 0, then that become z0 dot, and after that this become minus f dot t, and z0 if you substitute from here, then finally it is not difficult to see that this algorithm is exactly converted like some kind of algorithm that is looks like the super twisting algorithm eta 0, and after that I have plus z1, and obviously one term more term will come here, that is f dot t, and second term is z1 dot equal to minus lambda and signum, and here I have eta 0. Now, one more transformation you have to do. Why one more transformation? Because in super twisting algorithm, first part we don't have any disturbance. So, suppose that if you write z1 dash equal to z1 minus f0, so z1 dash will come here, and z1 dash that is equal to here nothing but z1 dot, that is minus lambda 0 signum eta 0 and plus obviously here a negative sign. So, after that I have double derivative t, and due to that reason, in order to make convergence of eta 0 and z1 0 dash, I have to maintain bond on f double dot 0. If we are able to do that, then it is possible to show that eta equal to 0 and eta dot equal to 0, and obviously whenever eta equal to 0, then z equal to f0 dot t. And what is meaning of eta dot 0? if eta dot equal to 0, then it is not difficult to see that f0 dot is z0 dot. Okay. So, in this way I can able to prove the convergence of algorithm. Okay. So, now what is our main goal? Exactly the same like super twisting algorithm, I have to design lambda 1 and lambda 0. And how to design? You can either apply the theory of Professor Levant, or that is based on measurement curve, or you can apply some kind of theory that is given by Professor Levant based on strictly Lyapunov function. Okay. Here I am going to give theory that is developed by Levant, okay, because that is based on homogeneity and contractivity. Okay, and things are very easy, just you have to maintain everywhere homogeneous, then things are very easy to follow. Okay. So, it is possible to show that in absence of noise, I am assuming that whatever signal I am going to apply here ft, that is noise free. Okay. So, that is exact signal f0, but in that particular case it is possible to show that I can able to, if I am able to design gain like this, then what kind of things happens, that I can able to prove that basically z0 equal to f0 t. One more important thing, whenever I am doing this kind of manipulation, at that time I am assuming that ft is containing f0 t, but obviously whenever I have error, then one more error term will come here, and that error is finally transferred here. Again, since I am assuming that error is bounded and Lebesgue measurable, so again some condition will appear, and due to that reason that is not going to affect any other analysis. Okay. So, main theme is, you can see that the double bond f dot t, that is less than L. So, that constant you can select to design lambda 0, that is gain associated with the second term. Okay, that is going to compensate the uncertainty, and after that lambda you can able to select, that is based on this particular expression. Then it is possible to show that you can able to get the derivative. So, in computer system you have to actually run this particular algorithm, and you have to keep this signal, and after that how to measure the derivative. So, z1 just you can measure. Okay, z1 if you are going to measure, then you will get the derivative of the signal. Okay, I hope that you are able to understand my point. So, what is highlight? Since super twisting controller avoid the chattering of first order system, okay, so it means that I can also able to utilize this kind of concept, exactly same kind of concept for the differentiator design. So, you can see that during this construction I have started with first order system. Okay. And then we have proceed towards the differential process. Okay. And proposed differentiator handles some kind of non-smooth signal and measurement noise. Okay. Finite time is guaranteed because this is somehow super twisting algorithm, and obviously relative degree of differentiator is 2. So, using this kind of differentiator whatever I have proposed, so this is the differentiator that is only applicable for the calculation of the first order derivative. Okay. Now, this is very important to show that in presence of the noise our differentiator accuracy is good enough. That kind of things I have to establish, because we know that same kind of job I can able to do using Utkin's differentiator or high gain differentiator. But why we are actually making some extra assumption, because here in this process you might have seen that I have to make one more extra assumption that this is less than L. It means that not only derivative of signal but their double derivative also should bounded, then only I can able to propose some kind of super twisting like differentiator. So, it is possible to show that if Z0 minus F0 is bounded by this. Why I am telling about this? You can see that in original differentiator, since you are going to apply some kind of signal, so what happens that whenever you are generating some kind of differentiator, suppose that this is computer system and this is your plant. So, whatever sensor information coming here, directly you are going to keep inside the differentiator. So, this FT signal is corrupted signal, and due to that reason whenever you are going to measure Z minus F0, so somehow this signal come with some kind of accuracy. Now during the differential process, it is possible to show that if that will follow mu1 epsilon, then after differential that will become mu2 epsilon power half. Okay, this is just due to the homogeneity. Okay, we have already seen that whenever I have super twisting algorithm and if sampling interval is tau, then accuracy of x1 is actually bounded by tau square. Okay, what is accuracy of x2? X1 dot, that is proportional to O. In big O notion you can able to write like this. And if x1 contains some kind of noise, at that time accuracy is given by x1 and obviously some kind of big O notion epsilon, and x1 dot, that is big O epsilon power half. So exactly same kind of consistency is also here. Okay. Now how to prove it? So proof is not difficult. What you can do? You can create eta 0 and eta 1 is nothing but z1 minus f0 dot. You can define it and after that you can construct this kind of differential inclusion. Why differential inclusion comes into picture? Because here I have somehow lambda 0 signum eta and plus f double dot, f0 double dot term will appear here. So and I know that f0 double dot t, that is bounded by L, and due to that T is lambda 0 minus L and here lambda 0 plus L. So I have infinite many differential equation here. So this is nothing but some kind of flip of regularization I have used. And now what I am going to do, I am going to apply some kind of coordinate transformation. So now I am also going to include some kind of noise. So how to include the noise? Because if f0 is not exact, so obviously eta 0 contains some kind of noise that will lie between minus epsilon to plus epsilon. So everywhere I am going to substitute that. Now whenever I have this kind of differential equation, obviously I cannot able to converge exactly to eta equal to 0 and eta dot equal to 0 in finite time t greater than equal to t. So what we have observed that whenever we have some kind of noise, then obviously I can able to converge in the vicinity of the eta 0 and eta 1 zeta 1. That is the property of the homogeneous equations, that in presence of some kind of noise, and here if you see carefully, then noise is inside this particular variable, so that is not going to destabilize our system. Okay, so homogeneous differential equation is somehow robust in presence of the noise. So same kind of theory we have applied here, and after that we have calculated this bond. Now exact bond I can easily able to get. How to get? Since I know that this particular differential equation is homogeneous. So how to maintain homogeneity? Provided this eta 0 is actually contains same degree of homogeneity like zeta 0 contains same kind of homogeneity like eta 0. Okay, and due to that reason same kind of scaling factor I have used here. It means that somehow magnitude of eta can be represented by alpha square into zeta, and in this way I can able to get the alpha in presence of the eta 0 that is known to us and actual value of eta, and finally I will get this kind of bond eta and eta 1. Okay, so in this way also I can able to see that eta 0 is proportional to epsilon, because whatever error here I have, that is epsilon, and this is proportional to square root of epsilon. Okay, so using this simple transformation I can able to talk about the accuracy of this particular differential process. Okay, so what is implication of this transformation? Since due to homogeneity, system is going to preserve their structure. What is meaning of preservance? It means that if I will scale with this, then still our differential equation is remains the same. So by scaling this I can able to come to the very close to origin by making alpha very small. Okay, and due to that reason I never become unbounded. Okay, now eta 0 and eta 1 scaled by zeta and square root of zeta. Okay, and in this way I can able to talk about the stability and bonded in presence of the noise. So homogeneous transformation gives us systematic way what kind of response we will see in presence of the noise. Now another important factor, how to design gains, because signal is going to vary but algorithm is remains same. It is possible to show that if by simulation you will get one set of gain, easily you can able to scale that gain by some kind of parameter L greater than equal to 0, because everything is homogeneous. So just you can also scale the gain, all other property remains the same, and in this way basically accuracy is going to affect. Okay, so in order to maintain accuracy you have to now select this L very carefully, that is the meaning. And again proof is not very difficult. What you can do, suppose you have some signal f, you can divide that by L, initially L equal to 1. So for that I have designed 2 gain, because 2 gains are required for the convergence of differentiator. Now I am going to scale it out. Okay, and after scaling it is possible to show that again I have homogeneous differential equation. And how to get homogeneous differential equation, because here whatever lambda 1, since z 0 tilde and f tilde is scaled by this, and due to that reason this particular factor comes into picture, then we can able to make sure that this equation when L equal to 1, that is exactly when L equal to greater than 0. In this way I can able to design different set of gain by considering just one set of gain. And one of the valid set of gain we have already seen, that is given by Professor Levant using the measurement curve method, and somehow this gain several times I have repeated that this gain is very optimal. Second set of gain also provided by Professor Utkin only, that will give very optimal convergence in somehow. So whenever you are doing some kind of practical implementation, practical system we are designing based on differentiator, it is better you can utilize this kind of gain that is actually given by Professor Utkin, Professor Levant. Okay. So V become noisy, Z1 remains legit, but a small phase delay is always there. Okay, so delay kind of things also that is compensated, because these kind of homogeneous differential equation is robust with respect to delay. We have already seen that. Now in order to show the performance comparison, what I am going to do, I have taken some kind of signal. Here this signal do not contain any noise, and then we have developed some kind of high gain based differentiator. So some kind of low pass filter I have designed, and after that now you can see here that I have added some kind of noise, and frequency of noise I am going to increase. Then we are trying to check the actually accuracy of the proposed differentiator. So if there is no noise, you can see that both the algorithm is performing approximately same. So this is proposed differentiator, and this is actually the linear one, and this is true one. Okay. Now what I am going to do, I am going to increase the noise. Okay, and in presence of noise you can see the behavior now. Okay, now further you can increase. Now as frequency is going to increase, things become more prominent. It means that differential process you are going to lose if you have very high switching frequency noise, and that is also theoretically one can easily able to see that during differential process 30 is going to multiply here, and due to that reason what happens that if your differentiator is not robust, then that kind of effect will come into picture, and most of time we have high switching frequency noise. It might possible this is 500, 600, 1000, something like that. Okay, and due to that reason it is better to utilize the robust exact differentiator that is based on the super twisting algorithm, and gain set we have also given. Okay, and obviously theorem established the finite time convergence and accuracy, because one of the main intention to show accuracy in presence of the bonded level measurable noise. Okay, L will maintain the performance. Okay, so if correctly you can able to identify L, then your performance of your differential algorithm is very high, and practical tuning of this differentiator is also very easy, because most of time whenever some engineers are working, they are not worrying about the theory. They just worry about the gain, which set of gain I will use such that I will get robust, accurate and suitable real world application. So, for that we have already discussed how to select the gain. Now, next part of this lecture is basically based on how to design controller. So, I have second order system. So, relative degree 2, what is meaning of relative degree 2? You can take output equal to sigma and you can calculate the second derivative, then control is going to explicitly appear. Okay. Here I am assuming that A and B both are not exactly known. Now, again what I am going to do? I am going to take the information of the output sigma. This whole algorithm is going to run inside the computer. Okay. And from computer I will get now information of, I am giving sigma and I am getting information of sigma dot. Okay. So, sigma dot is nothing but we have already seen that is equal to Z1. So, sigma and Z1. So, here sigma dot equal to Z1. So, now whatever Z1 I have to take out from the computer system, that will give the derivative of sigma. I am going to utilize that information to design the robust control. What is beauty? This control, since now whatever information we are going to utilize for the control design, so accuracy will also satisfy. Okay. And due to that reason, it is possible to show that whenever you apply two sliding mode control, that is based on differentiator, exact stabilization you are going to get, finite time convergence you are also able to get in absence of noise. In presence of noise, you can able to see that your trajectory remains very close to the origin sigma dot equal to 0. Suppose that if I am solving just a stabilization problem, because epsilon is very small. Okay. So, I have taken this practical system, C sigma equal to x1, that is output, Km and Km maximum and minimum value of the control which through which control is going to enter, that I have selected. I have designed this kind of differentiator, okay, based output feedback. So, actually you have to somehow dynamic output feedback is needed. So, Z1 is nothing but the information that is coming from X, and what is Z1? Z1 is nothing but the output of this particular differentiator which is running inside the computer, and in this way I can able to get the dynamic output feedback. Why dynamic? Because you can see here Z1 is going to satisfy some kind of differential equation or differential inclusion. In this way also you can able to calculate the precision of the trajectory, okay, or steady state accuracy of the trajectory, and initial condition we have selected like this, and it is possible to show that all state is going to converge in finite time. Okay. So, in this way, just using the output and by taking one kind of differentiator, even if dynamics is not known, means dynamics is black box, I can able to design second controller for second order uncertain system. And obviously, whatever performance, that performance is much higher, because whatever differentiator I have used, that is robust and exact. Okay. So, two sliding mode control with differentiator achieve obviously finite time stabilization in presence of very small noise, means bonded or Lebesgue noise, and after that differentiator is also exact. Exactness we are characterized in terms of the epsilon, and simulation we have already seen that performance is extremely good in presence of the disturbance. So, in this way I can able to utilize this kind of concept for any second order system. Okay. So, with this remark I am going to end this class. Thank you very much.